Swayam Prabha. Digital India. Educated India.
Okay, so let me get started with today's class. Today what we are going to do is that we are going to look at what is called as a Nyquist plot, right? So if you recall what we have been discussing, we have been looking at frequency response. And what was frequency response? It is the response of the class of systems under study to sinusoidal inputs, right? And we saw that if we have stable LTA systems, if we give a sinusoidal input of frequency omega, the steady state output was also a sinusoid of the same frequency but scaled in amplitude and shifted in phase, right? And the entity that becomes extremely important in that case is what is called as a sinusoidal transfer function, right? G of j omega, right? So that's what we have been looking at. And what we have been doing is that we learned about the Bode plot, where we figure out how to graphically illustrate or represent the sinusoidal transfer function in terms of the magnitude and phase, right, as omega varies from very low frequency to very high frequencies, right. So that's what we did in the Bode diagram. So the Nyquist plot is once again a visualization of the sinusoidal transfer function, but a slightly different visualization. Okay, we will see what this is. Okay. So what is this Nyquist plot? Okay, so a Nyquist plot is nothing but the plot of g of j omega, which is a sinusoidal transfer function, okay, in the complex plane. That's it. So it is pretty straightforward to understand. So what we do is that we essentially plot the real part of the sinusoidal transfer function versus the imaginary part of the sinusoidal transfer function in the complex plane. Okay, so that is the Nyquist plot. Okay, so some people will call it as the G of S plane. Okay, to indicate that it is no longer the S plane as such. That is, we are not tracing the variable S, but rather we are tracing the transfer function, right? G of S, right? So that's also a complex valued function, right? So people will call it as the G of S plane or G of j omega plane and so on. So it is essentially the plot of the real part of G of j omega versus the imaginary part of G of j omega, as omega is vary from 0 to infinity. Okay, so that's what happens here, right? So as we vary omega from low frequencies to high frequencies, what happens to the real part and the imaginary part? Okay, so when we ask the question, see, what is the application of this Nyquist plot, right? How do you use it in practice? We are going to look at that, right? And we are going to see how the Nyquist plot can be used for even stability analysis, right, and even control design. Okay, so that's something which we are going to look at as we go along. Okay, so what we will do is that we will once again construct the Nyquist plot of individual blocks that we have been learning, right, and then we will identify some difference between the Nyquist plot and the Bode plot, okay, as we go along. Okay, so let's start with of course I am not starting with a constant, because a constant is just plotted on the real axis, right. So if I take my first building block as k, like what we did in the Bode diagram, so that k is going to be either plotted on the positive real axis or the negative real axis depending on its sign, right. So that's pretty straightforward. Okay, so what happens from the other factors onwards? Suppose let's say I consider 1 by s, right, which was another factor that we considered. So then what happens? G of j omega is going to be equal to 1 divided by j omega, and this can be rewritten as minus j by omega. Do you agree? Correct. So I just multiply and divide by j. I just write it as minus j. So this I can write it as 0 plus j times minus 1 over omega. So essentially what I am doing is that I am just writing as the real part and the imaginary part, right? And even I can follow an alternative representation of complex valued functions, right? I can write their magnitude and phase, right? Correct? So I can write this as, what is the magnitude of this function now? 1 by omega, right? What is its phase? It is going to be minus 90, right? So that's what we are going to get, because so you see that the function is always going to be on the negative imaginary axis, right? So the plot of this particular factor, right? So consequently I can rewrite like this, and so if I want to plot this, right? So how will this look like? So let's say I plot this on this g of s plane, right? So what will happen as omega starts from 0, where are we going to start from? So essentially I am going to start from minus j infinity, right? And as omega tends to infinity, where am I going to end up with? I am going to end up at the origin, right? So that's what is going to happen. So essentially what's going to happen is that the Nyquist plot of this particular factor is going to be along the negative imaginary axis. This is omega tending to 0, and this is omega tending to infinity, right? So that's the Nyquist plot of 1 by s, okay? So that's what happens here, right? So now let's essentially plot for a few more factors, then we will discuss a few points, right? So now let's plot it for the derivative factor. G of s is s. So then g of j omega becomes j times omega. So this I can rewrite it as, once again, 0 plus j times omega. So 0 is the real part, j omega is the imaginary part, right? So in terms of magnitude and phase, what will happen? I can rewrite this as omega times omega and plus 90 degrees, right? So that's what is going to happen. So what's going to happen to the Nyquist plot of this particular factor at very low frequencies as omega tends to 0? Where am I going to start from? I'm going to start from the origin, right? Because the value becomes 0, and as omega tends to infinity, I go to infinity along the imaginary axis, okay? So that's what is going to happen. So for this, the Nyquist plot is given in green, right? So you see that it's just along the positive imaginary axis, okay? So that's what happens for this derivative term, okay? Right, okay. So now let's go forward and then look at other factors, right? So what is the next factor that we considered? G of s is 1 divided by Ts plus 1, right? So this I can rewrite if I want to figure out the sinusoidal transfer function. This can be written as 1 divided by 1 plus j times t omega, right? Correct? So if I multiply and divide by the conjugate and then simplify, what will I get? If multiply and dividing by the conjugate, which is going to be 1 minus j times t omega, I am going to get 1 divided by 1 plus t squared omega squared minus j times t omega divided by 1 plus t squared omega squared. Do you agree? That's going to be the real part and the imaginary part, okay? So in terms of magnitude and phase, how can this be rewritten? What do you think will be the magnitude of this transfer function? It's going to be just 1 divided by square root of 1 plus t squared omega squared. See, by now I think I'm sure all of us are getting more and more comfortable, right? So you look at the function itself, right? So if you have this complex valued function, you want to find the magnitude. It's just the basically you just take the you have a ratio, you just take the ratio of the individual magnitudes, right? So that's what you have, right? So you just do that, and what's going to be the phase? Once again, it's going to be the algebraic sum, right? So what's going to be the phase here? The phase is going to be minus tan inverse of omega t, right? So that's what we are going to have for this particular factor, right? So that's what we get. Is it clear? So now I'm just going to essentially help you with something, you know, like which is a good practice in plotting Nyquist plot. So you will see that, say, as opposed to a Bode diagram, you know, like for when you want to plot the Nyquist plot of a general transfer function, it's a little bit more challenging, because In the Bode plot, what we did, you give me any transfer function, I break it down into those individual blocks and then essentially plot the magnitude and phase plot of the individual blocks, add them, that is it, right. So, the technique was pretty what to say, straightforward, right. So, but we need to of course be careful in plotting the individual factors of Bode diagram, right. But in Nyquist plot, we do not have that what to say luxury, right. So, you give me a higher order transfer function, I need to essentially plot it as it is, right. So, it becomes a little bit more challenging to do it by hand, okay. So, I am just going to essentially share a process which has helped me, like do these things, right. So, we are not going to look at Nyquist plots of very complex factors at least when we discuss things analytically, because I am not going to ask you to draw the Nyquist plot of like very high order factors by hand in your exams, okay. You can be assured of that. So, if I want you to analyze, I would ask you to use MATLAB, but we should know what the concept is, right. So, that is why I am teaching you the theory behind it, right. So, so one process which helps is to figure out what happens at critical frequencies, right. So, and the limiting frequencies and even some frequencies in between, right. So, let us do that. So, typically it is useful to construct a table, like as to what happens to the real part of g of j omega and the imaginary part of g of j omega as we vary at various critical points, critical values of omega, and also its magnitude and phase, okay. So, let us say we construct a table like this, okay. So, as omega tends to 0, what do you think will happen to the real part and the imaginary part? Look at the real part. What is the real part? 1 divided by 1 plus t squared omega squared, right. As omega tends to 0, what do you think is going to happen to this? It is going to go to 1, right. What can you say about the imaginary part? 0, right. Please note that the imaginary part is always going to be negative, right, and the real part is going to be positive. So, in the complex plane, in which quadrant is this Nyquist plot going to lie? See, you can see that for all omega between 0 and infinity, because capital T obviously we take it to be, of course, we take capital T b to be greater than 0 for this discussion, right. So, you can immediately observe that the real part is always what to say, I would say non-negative, and the imaginary part is always non-positive, right, for all values of omega between 0 and infinity, right. So, which quadrant do you think the Nyquist plot of this factor would lie in? In the complex plane? In this quadrant, all right. What is this quadrant called as? 1, 2, 3 or 4? Fourth quadrant, right. So, that is what it is, right. So, essentially you will see that the Nyquist plot will lie in this quadrant, right. So, that is what will happen. So, now you tell me, right, what happens to the magnitude of g of j omega as omega tends to 0? Obviously, it is real part squared plus imaginary part squared, and then take the square root. So, the magnitude is going to be 1. What about the phase? It is going to be 0 degrees, all right, as you go to 0. Now, is there any other critical frequency, like having drawn the Bode diagram, can you think of any other critical frequency for first order factors? So, it is the corner frequency, right, 1 by capital T. What happens is 1 by capital T to the real part and the imaginary part? You see that the real part becomes 1 by 2, the imaginary part becomes minus 1 by 2. Of course, I am not writing j. If you are very particular, you can write minus j by 2, but I am just writing the component, all right. So, j is, it is understood that we have the j, right. So, then what happens to the magnitude and the phase? Magnitude is 1 by root 2, all right. What about the phase? It is going to be minus 45, right, that is what else going to happen. So, let us continue this table, okay. Okay. So, now as omega tends to infinity, what do you think is going to happen to the real part and the imaginary part? Both will go to 0, right, 0, and what do you think will happen to the phase? It will essentially go to minus 90, we will see why. Okay. So, we are going to interpret it in a different way, okay, like we will see why that happens. It happens like this. Okay. So, that is something which we will figure out when we draw the Nyquist plot. So, let us construct the Nyquist plot, right. So, and then see what happens. So, I have the real axis, the imaginary axis, right. This is the G of S plane, and we want to plot the Nyquist plot, right. So, now if I want to plot the Nyquist plot of this function, right. So, I know that there are certain critical points, right. So, 1 is one critical point, 1 by 2 is one critical point, right. So, because at 1 by when at frequency of capital 1 by t, you know, like we are having the real part as 1 by 2 and the imaginary part as minus j by 2, right. So, and then like 0 and 0 is also important because that is what happens when omega tends to infinity, alright. So, this is omega tending to 0. Now, what happens to the Nyquist plot of this particular factor? Okay, we have identified 3 points, right. Now, I need to draw a curve which passes through these 3 points, right. So, of course, you know, like given these 3 points I can draw so many curves, right. So, we will see that this Nyquist plot has one specific structure, right. How do we get that, right. So, let us try it out. So, what we will do is that like you evaluate and tell me what you get when you take the real part, which is 1 divided by 1 plus t squared omega squared, subtract half from it, take the square, and then like you take the imaginary part square, which is minus t omega divided by 1 plus t squared omega squared, and square it, and then like if you equate it, what do you get? Can you quickly solve and tell me? Yeah.
Here imaginary part is minus t omega times real part, right? The imaginary part is equal to minus t omega times the real part.
Minus t omega times the real part, yes.
So, if you are plotting imaginary part versus real part, it will just be a set of lines which slope minus t omega, and as omega keeps varying, the slope keeps
Okay. So, you are see you please note that the real part and the imaginary part are parameterized with respect to omega. So, in fact, what is going to happen is that what you are saying is correct if I plot for a particular omega and I vary the real part, but it does not work like that. See, what you are saying is that you are saying imaginary part is minus t omega times the real part. Okay, if you plot real and imaginary, if you take the real part on the abscissa and the imaginary part on the ordinate, you will essentially get a series of straight lines, you know, like for any for a family of omega. But then we are not varying real part. See, real part is not the independent parameter here, omega is. So, for a given omega, the real part is not under our what to say control, you know, we get what it is. Is it clear? Okay? Yeah. So, please you will understand why I did that, right. I am asking you to evaluate it. Kindly simplify this and tell me what answer you get. Yeah. See, I have given you this because I a priori know what is the answer, right. So, I am just asking you to do it and tell me. One by 4, right. I have rewritten it as 1 by 2 whole square. Okay. So, what does this equation correspond to? So, if you recall our geometry, right. So, what is such an equation? It essentially this equation will trace out a circle, right, which is centered at 1 by 2 comma 0, right, and of radius 1 by 2, right, and that's what is the Nyquist plot here. Okay, so this starts like this. Okay, of course I am drawing a freehand diagram, so please pardon if it doesn't look like a semicircle, you know, like so. Essentially it goes something like this, right. So it's so the Nyquist plot of this factor is going to be a semicircle, you know, like which is essentially going to be centered at 1 by 2 and starts at 1 0 and ends at 0 comma 0. Okay, so that's going to be the Nyquist plot. So the I am going to draw an arrow like this to indicate what happens as omega increases from 0 to infinity, right. So that's what is the Nyquist plot of this particular factor 1 by t j omega plus 1, right. So that is the Nyquist plot. Okay, is it clear how we got it? Of course, when we ask the question, hey, how did you get this in the first place, right? How did you pull out, you know, this equation and write, you know, like, of course that comes with experience. Okay, so there is no hard and straight answer to that. That's why, you know, plotting Nyquist plot is both art and science, right? As you keep on doing more examples, you get an intuitive feel of what would happen, you know, how that factor would look like. And sometimes it's going to be very non-intuitive, you know, I will tell you why, right. So that will become clear as soon as we plot the next factor. Okay, so that's something which we will discuss shortly, right. So it so happens that the Nyquist plot of this 1 by ts plus 1 is going to be in the form of a semicircle of radius 1 by 2. Okay, so that's the Nyquist plot. So we will gain some insight into this process and why Nyquist plots, you know, like are a little bit more challenging, you know, like once we do the next factor, which is the reciprocal of this 1 by ts plus 1, right. See, when we plotted Bode diagrams, right, what did we observe? If we have two factors which are the reciprocals of one another, what happened to the Bode diagram? They happen to be just mirror images or reflections about the 0 decibel line, right. So based on how we took it, right. So essentially our low frequencies values were the 0 decibel lines. About that line, it was just a mirror image. Of course, we need to be careful there, right. So of course, if I took 1 by s and s, it's also a reflection about that 0 decibels and omega equals 1 point, right. So it just gets flipped about that, right, about the 0 decibel line which passes through that point, right. Okay, so now let's see what happens in the Nyquist plot, right. So this is g of s. So what happens to g of j omega? It is essentially 1 plus j times t omega. So this will give me the magnitude as 1 plus t squared omega squared, and the phase is going to be just tan inverse of t omega. See, by the way, before we go any further, I hope it's clear why this phase was minus 90, right. So you look at how this curve comes to 0. So if you look at how this Nyquist plot comes to 0, approaches the origin, you see that it approaches the origin. If you zoom in at the origin, it comes in like this, right. So if you zoom in further and further, if you draw a vector from the origin to that curve, that's going to be at an angle of minus 90. Okay, so that's how we put, that's why I put minus 90 there. Is it clear? Okay, why this happened, right? So that is the reason for the phase becoming minus 90 as omega tends to infinity for the factor 1 by ts plus 1. Okay, so this is what happens here, right? And now let's construct a similar table, right? Omega, real part of g of j omega, the imaginary part of g of j omega, the magnitude of g of j omega, and the phase of g of j omega. Okay, so let's construct a table in this manner. Okay, so let's start filling in this table using a similar approach. Okay, so let's say as omega tends to 0, what happens to the real part and the imaginary part? 1, 0, 1, 0 degrees, right? The magnitude is 1, phase is 0 degrees. So at omega equals now 1 by t, what happens? You will get 1, 1, right? Root 2 and 45, correct? Then as omega tends to infinity, what do you get? 1, infinity, infinity, 90, right? That's what you will have. Am I correct? Okay, so I am just looking at the equation above, that's all we are doing, right? See, this is the real part. See, if you look at it, the real part is always 1 for this particular factor. The imaginary factor, imaginary part is t times omega, right? The magnitude is this and the phase is this. Okay, so you see that I am just calculating for various omega, I am just writing the values down. That's all we are doing. Okay, like nothing extraordinary here, right? So just pretty straightforward. So now if I plot the real part versus the imaginary part in the G of S plane, what are we going to get? What will happen? At omega equals 0, let us say we start from 1. So please note that the real part is always 1. You could readily observe that, right? So because you can see that the real part of the sinusoidal, this factor is always 1. So what can you say about this curve? If the real part is 1, what can we say? And the imaginary part is always non-negative. So what can we immediately say about this one? This is going to be a vertical line, right, starting at 1, 0 and then just going up, which is parallel to the imaginary axis. This is what happens as omega tends to infinity, right? At omega equals 1 by t, it's going to be j. Alright, so that's what is going to happen. Okay? Sorry? Is this correct? At omega equals 1 by t, the real part is 1 and the imaginary part is j, right? And so the magnitude is going to be root 2. Okay, then the phase is going to be 45 degrees, right? So I am just drawing it on the same curve, right? So just to convince ourselves that that is the case. So you see that this is the Nyquist plot of the factor Ts plus 1. Now you look at the Nyquist plot of the factor 1 by Ts plus 1 and Ts plus 1. Can you draw some conclusions like what we did in the Bode plot? No. Right, one is a semicircle, another is a straight line. So now you understand, like why progressively we are slowly understanding, right? Why the Nyquist plot is drawing a Nyquist plot is a different ball game, right? And sometimes it is a bit of a challenge, right? So in Bode diagram, like if you had like reciprocals, like we immediately flip the curve, right? So and we could immediately process it and go on. But here it's not so straightforward because the shape itself is different.